The idea and the practice of turning salt water into fresh drinkable water is old news, really old. Aristotle mused about desalination in the 4th century BC. Here's what he wrote. Salt water, when it turns into vapor, becomes sweet, and the vapor does not form salt water again when it condenses. In the 2nd century, probably even earlier, Greek sailors did exactly what Aristotle was talking about. They boiled seawater in bronze vessels and trapped the rising steam in sponges hanging above the cauldron. When the sponges were saturated, they squeezed the precious liquid into storage jars. And even the Old Testament mentions desalination. Well, kind of. When the people following Moses grumbled that they were running out of drinking water, he threw a log into a brackish spring and, with a little divine intervention, turned it into fresh water.
Nice intro, Steve.
Thanks, Rachel.
I like how you worked in a quote from Aristotle, too. Very classy.
Well, you could even say classical.
Well, I could, but I think I'll leave the puns to you. It's pretty interesting, though. I hadn't really thought about how old desalination is.
Well, you might also be surprised to learn how widespread it is. Today, there are thousands of desalination plants in 150 countries that produce almost 30 billion gallons of fresh water every day. The technology is a fixture in the global effort to supply water for a huge chunk of the world's population that struggles to find clean water. But it has its limitations.
I knew there had to be a catch.
Well, it's expensive, arguably the most expensive of all water supply alternatives. Estimates generally put the cost of desalinated water at $3 to $4 per 1,000 gallons, which is a lot pricier than options like stormwater recovery and water recycling and reuse.
Okay, so now that we understand the problem, we can get to my favorite part, the research. Maybe we should introduce ourselves first.
I'm Steve Franzel.
And I'm Rachel Robertson. From the College of Engineering at Oregon State University, this is Engineering Out Loud.
So earlier episodes this season have emphasized the absurdly small amount of accessible, fresh, clean water on the planet, but I think it bears repeating. Of the unimaginable volume of water on, in, and above the Earth, we humans rely on only 0.75% for our survival, and much of that we squander thoughtlessly, until all of a sudden we notice that it's disappearing, or just gone.
That's why I was really excited to find out that we have a researcher here at Oregon State who is working on the age-old problem of desalination, so that more people facing water scarcity can have reliable access to clean, fresh water. His name is Bahman Abbasi. He's an assistant professor who works at OSU Cascades in Bend, and he just received a $2 million award from the Department of Energy. And over the next 3 years, he'll be leading a team of researchers to develop a modular, portable, self-contained desalination plant. We got the opportunity to talk to him when he was in Corvallis, and one thing that impressed me was the passion he brings to his research. I asked him why this project is so important to him.
A lot of people are needlessly suffering because of water scarcity. There's a lot of water pollution, and even here in the U.S., look at Flint. The tragedy that unfolded in Flint was a big motivator for me. In order to cut costs, the Michigan government did something inexcusable, but it doesn't have to be like this. It is really heart-wrenching when you see these people, these children, suffer, agricultural products suffer, their livelihoods suffer, when 70% of the planet is water, if only you could use it.
Finding a better way to use salt water is the focus of a national effort by the Department of Energy, which has committed $21 million for 14 different projects, of which Bahman's is one. The purpose of this program is to accelerate the development of solutions that are more accessible and affordable to communities in desperate need of reliable, fresh water, including areas that are not connected to the electric grid.
The problem is that because of climate change and climate patterns, the amount of water that is distributed between different locations is changing. A lot of wet places are getting a lot wetter to the point of floods and a lot of undesired consequences. And a lot of the drier places getting much, much drier. And this change in distribution of water brings severe scarcity to certain regions. And it is fortuitous that a lot of these regions have large bodies of salt water or brackish water nearby. So if we have technologies that can use seawater to produce potable water in an efficient, modular, portable way, it can solve a lot of humanity's problems.
Here in the rainy Pacific Northwest, water desalination is not something we spend a lot of time thinking about. So the question in my mind was, how do they even do this? Bahman explained that there are two different approaches to desalination.
Very broadly speaking, there is the thermal way, by heating the water and basically distilling the water. There is the membrane-based technologies that people force water through semi-permeable membranes where salt is kept on one side and clean water is allowed to pass through the membrane. So we have two routes to do it, membrane-based and thermal-based.
Among the various thermal-based desalination processes, the oldest and most common is distillation, which is how those sailors made their own fresh water supply, using the sun as their source of power.
Both methods use a lot of energy. Because oil-rich countries like Saudi Arabia have plenty of that, they use the thermal method, burning fossil fuels to heat and then distill water. Desalination plants in the U.S. tend to use a membrane-based technology called reverse osmosis, which also uses a lot of energy and is only economically viable for really large plants because of the efficiencies of scale. And as Steve mentioned at the beginning, large plants are very expensive to build, and the water they produce has to be pumped over long distances.
In order to solve these problems, we need to make water production very modular and portable. So it's closer to the point of consumption. So it's not just point source. You can take it where you need it. And that brings a lot of challenges. You lose the advantage of size. In a lot of engineering systems, the bigger you make them, very roughly speaking, the more efficient, cost-effective they become. So if you shrink them, you lose a lot of your efficiency and a lot of times a lot of your cost competitiveness. So one of the biggest challenges was, how do you shrink the size of the system without sacrificing your energy efficiency and while maintaining your economic viability? The way that my proposed technology is different is it is thermal-based but efficient.
And just to break in here, under the right circumstances, Bahman's proposed system can operate independently from the electrical grid by tapping solar power.
It is also small scale and modular and portable. So you have modules that are like half a typical desk in size, and you can stack them up and have your desired throughput, your desired production, put them in containers and ship them around to where you need them. They don't need to be permanent installations. They don't need a lot of electricity. They're pretty much self-contained, so they can produce water where it is needed.
More specifically, Bahman's system will use high-speed air jets to atomize and evaporate incoming salt water.
It's kind of like how if you blow too hard on a bowl of soup, how it just splashes all over the place. It's the same phenomenon.
I love the imagery of that, but I still wasn't quite getting it.
Let me try this. Imagine you have a puddle of water, seawater, and you inject high velocity air jets from the bottom of it. You atomize it, and in the process, it gets evaporated.
Now you're left with humidified air that's laden with water and salt particles. Later in the process, the humid air is dehumidified by cooling it. The fresh water condenses out, and the salt is collected separately.
So you can use your air as a conveyor, and you can, not easily, but you can get the humidity out of it. The point is, we don't distill, we humidify and dehumidify. And that little distinction gives us a lot of energy and efficiency advantage.
One of the technological advancements in Bahman's system will be that less energy will be required compared with other desalination systems that use humidification and dehumidification. In addition, the process will allow the heat required to humidify the air to be recovered, so very little energy is wasted. The air is recycled so that it can be used again to absorb more moisture in the humidification phase.
But how all that works is part of the technology that Bahman is still working on and hasn't patented yet. So he has to be careful with how much he reveals.
People have been doing this, but the traditional systems to do this have major problems. They have a lot of fouling problems. They need air blowers. They need water pumps. And I designed ways around all of those problems in order to maintain the advantages, the energy and cost advantages of a humidification, dehumidification process without the drawbacks of fouling and requiring a lot of electricity.
What Bahman means by fouling is that the salt gets deposited everywhere in the system and clogs things up. Shutting down the system to clean it would mean losing efficiency. This is where his modular system has an advantage. In the case of fouling, just one module can be shut down for cleaning, while the rest of the system keeps producing fresh water.
And his system also addresses environmental issues. Other desalination systems produce a concentrated brine at the end of the process. It's called waste brine, and typically it's twice as salty as seawater. Usually that super salty brine is just dumped back into the sea, but that can severely harm marine life, unless it's sprayed over a large area, which is, of course, expensive and inefficient. The final byproducts of Bahman's system, though, will be fresh water and salt solids, no brine. That's called zero liquid discharge.
So we get all the water out, and the other byproduct is just solid salt. And salt has value. You can sell it as a side revenue, and seawater has predominantly sodium chloride, table salt, which is sellable but cheap. But most importantly, it has magnesium chloride, which is the feedstock or the base material to produce magnesium metal. And basically, all of magnesium production in the US is done from magnesium chloride, which is found in seawater. So when we succeed, I'm not going to say if, when we succeed and we have this zero liquid discharge, so just water and just solid salt, the magnesium chloride can be separated out and be used to produce magnesium metal. It's avoided environmental cost that adds benefit and distinguishes the process from others.
Okay. And so you feel pretty confident that you can do this?
Oh, yes.
So what gives you that confidence?
I've been working on this for a long time. I've been doing a lot of analyses and a lot of thinking on this. I've spent the last several years understanding what technologies have worked and why, what technologies haven't worked and why, and bring pieces together. It's still a research project, so there is a chance that something might go wrong. Fundamentally, there is no reason that it will not work. It will work. Whether or not it will be as energy efficient as I project it to be is a matter of design and research.
As we mentioned at the top of the show, this is a story that's just getting started, and we're planning on following this research to find out if Bahman is successful in achieving his goals of efficiency. I want to leave you with some more of Bahman's passion for his work, which also answers the question of why we should care about desalination here in the Pacific Northwest when we still have plenty of water.
A lot of major achievements come about from being outward-looking, trying to address problems that are not directly affecting me today, but is affecting my country, is affecting the world. I have a large proposal under review for treating fracking water. We don't do fracking in Oregon. The earthquakes in Oklahoma, it's none of my business, but I don't think about it this way. I think we should be, as an institution, as academics, outward-looking, not live in our own sphere, and I think can make for a much richer society, much richer institution, and a much more successful one. I would have not been able to bring in this award without collaborations with people all over the country, coast to coast, literally. If we do this, we can be successful and build a much richer and more successful community.
This episode was produced and hosted by me, Rachel Robertson.
And me. Sorry. Let's do that again.
This episode was produced and hosted by me, Rachel Robertson.
And me, Steve Franzel, with additional audio editing by Molly Ayton.
Our intro music is The Ether Bunny by Eyes Closed Audio on SoundCloud and used with permission of a Creative Commons Attribution license.
Other music and effects in this episode were also used with appropriate licenses. You can find the links on our website.
For more episodes, visit engineeringoutloud.oregonstate.edu or subscribe by searching Engineering Out Loud on your favorite podcast app.
Bye now, and stay hydrated.
What are you most excited about for this project?
I'm excited about getting a good night's sleep after it's all done.
Sounds good.